Um, when we went through that Desmos activity last week, Thursday, I know that it also introduced the notation for one-sided limit. So if you have the limit from the left or the limit from the right, there is specific notation for that. For this first example, it says find the limit as x approaches 0 of f of x if f of x is this piecewise defined function. So if it's equal to 0 for the x value is less than 0, it's equal to 1 for the x value is greater than or equal to 0. So I just wanted to show this function to you graphically. Not that you would have to graph this necessarily, but just show this to you graphically. What this function would look like. I'm going to grab a different colored pen that hopefully you can see. So this is saying when x is less than 0, the graph is the line y equals 0, or f of x equals 0. So horizontal line at 0, and only when x is less than 0. So it would look like an open circle then at 0, 0, and that part of the graph would be extending that direction. And then when x is greater than or equal to 0, the graph is the line y equals 1, another horizontal line. So you'd have a dot at 0, 1, and that would extend for x values greater than 0. So I just wanted to show you this from the graph. If we were looking for the limit as x approaches 0, this is the case like you saw in that Desmos activity, where as you approach 0 from either side, you're not approaching the same y value. You can see at the x value 0, the two pieces of your function have a different y value that they're approaching. So I would say for this piece here, this is how it would be written. So I'm going to show you the notation. I have it typed up below as well. I would say the limit as x approaches 0, and then it's like a little minus sign where you would write it as if it's an exponent on the 0. But that means the limit as x approaches 0 from the left. And that means the x values you're approaching are less than 0. So the limit as x approaches 0 from the left of f of x, that limit would be 0. Even though this function value here isn't defined at 0, 0, from the left, that is what the y values are approaching. So that limit is 0. The second piece would then be the limit as x approaches 0 from the right side. So then instead of putting a minus sign, you would see a plus sign. So this implies from the right. And that's same for x values greater than 0, because again, limits aren't concerned when x actually equals that number. So the limit as x approaches 0 from the right of f of x. So from the right side, those y values are approaching 1. And then overall, though, in this problem, so I'm going to look back here, the problem just says find the limit as x approaches 0. It does not say from the left or from the right. So when you just see the limit as x approaches a number, it's implied from both sides. So this implies from left and right. And if your left and right-sided limits don't approach the same number, the limit itself doesn't exist. So overall, I would say the limit as x approaches 0 of f of x does not exist. Any Mean Girls fans in here? The limit does not exist.
Is that from the right? Is it supposed to be equal to also?
No. So it is in the function. It's also equal to. But again, when you're just looking at the limit, it doesn't matter what the y value actually equals. Mean Girls. Have you seen the movie Mean Girls?
I feel like I've seen it.
Watch it. And it's at the end of the movie, so you have to watch the entire thing. The limit does not exist. It's about Mean Girls in high school. I know. My calc class 3 years ago, 3 years ago, made t-shirts, or they really wanted to make t-shirts. So they had a graph on the front that as x approached 0, the limit didn't exist. So it said the limit does not exist on the back, and the shirts were pink, and we wore them on Wednesdays. That class was all about Mean Girls. So. You have to watch it if you haven't seen it or don't remember the reference I'm talking about. Okay, so in general, what you're gaining from this is the limit. You do have one-sided limits from the left, from the right. In order for a limit to actually exist, then from both sides, you have to be approaching the same y value. So I have the definition below for one-sided limits, and the notation is really what I'm showing you here, along with the understanding, but notation you need to be familiar with. So the definition for the left-hand limit of f of x, need your attention up here, please. Left-hand limit of f of x as x approaches a, or the limit of f of x as x approaches a from the left is, and this is how it's written with that little minus sign. So if you see that, you are only looking at the limit from the left side if a problem has that symbol in it. And then we also have a definition for the right-hand limit as x approaches a, and that has that plus sign. So then I also have down here something I stated above. So when you see this symbol, that little minus sign there, you are approaching a from the left side, and that indicates you're only considering values of x that are less than a. And then when you see that plus sign, so you're approaching from the right side, you're only considering values of x that are greater than a. And again, a limit, I know I kept saying it yesterday, I'm going to keep saying it probably the entire time we talk about limits. It doesn't matter what's happening when x equals a. A limit, that does not matter just for a limit in general. It matters for continuity, which we'll talk about later. It doesn't matter just for a limit. And then this is important for you to understand here, what's in this box. So a limit as x approaches a, again, this implies from both sides. So the limit as x approaches a of f of x will equal some y value L if and only if the limit from the left equals L and the limit from the right equals L. So that's what I've been saying. Both the one-sided limits have to approach the same value in order for the limit itself to exist. So a one-sided limit will exist even if the entire limit itself doesn't exist, because a one-sided limit, you are just looking at the one side. So I do have an example with a graph, and I have 6 different limits it's asking you to find if they exist. If they don't exist, it doesn't say this in the directions, but we'll just write down the reasoning for why they don't exist. So what I actually might have you do, why don't you just look at these 6 and answer these 6 limits in your groups right now, or individually if you'd like to do that too, and then we'll just check them and make sure we're coming up with the same values. We did the Desmos activity, so you've already done this a little bit. It does not exist.
Would it have to exist though because they're the same? The actual value.
The actual function value.
They're trying to send me trades while I'm trying to use I have Miller on this. Yes. I tell you, the rest of your one that can actually project out. I'll take a good piece when we try to make two texts together.
All right. Check up here. Some of you weren't done with all of them when I started to walk around. So as you work with limits, what you're going to find is it's giving you again what x is approaching. It'll tell you if it's approaching from a specific side or if it's approaching from both sides. And you look at the curve where the curve is for those x values. So when x is approaching 2 from the left, this is your curve up here. So the left-sided limit should be 3. Right-sided limit as you approach 2 should be 1. Since these are different, the limit just as x approaches 2 doesn't exist. So if this asks you for a reason, because a lot of times, and this is how AP is going to work as well, it'll say if the limit doesn't exist, explain why. And in your explanation, you should be using correct notation for limits. So if I were to give an explanation, I would say it does not exist because, and this is one way I could write it, the limit as x approaches 2 from the left of g of x does not equal the limit as x approaches 2 from the right of g of x. Okay, so it's practicing using that notation. I've had students in the past write that into words. They'll just write out exactly what I said in words. This is what AP wants to see, though, is that you know how to use that notation. Okay, so practice that. Anytime you have to explain something, practice writing that out. And you're only going to really understand the notation and be able to use it later if you start using it now and practice with it. And then the last 3, notice they're all 2. So as you approach the x value 5, both right and left-sided limits approach the y value 2. Notice the actual function value g of 5 is equal to 1. That does not matter when you're finding the limit as x approaches 5 of g of x. The limit is 2, the function value is 1. Okay, so where the dot is doesn't matter. It doesn't matter if there is a dot. It matters again for continuity later on. It doesn't matter just for the limit. Any further questions on that? Okay. For the next example, here you're probably going to want your graphing calculators. It says find the limit as x approaches 0 of 1 over x squared if it exists. So I'm going to show this to you numerically. Okay, so work through it the way we did it yesterday with the tables. So I'm going to use that notation we just learned. I'm first going to find the limit as x approaches 0 from the left of 1 over x squared. So I'm going to make my table for that. And then I'm also going to find the limit as x approaches 0 from the right of 1 over x squared. Make a table for that. So again, you're just choosing, I'd say, at least 3 x values that are getting closer to 0 on either side of 0. So I could do from the left would be like negative 0.1, negative 0.01, negative 0.001. And then from the right of 0, positive 0.1, 0.01, 0.001. And again, that shortcut, to make it easier to substitute in values, type in the function into your y equals. So 1 divided by x squared. Go to your table feature, so second graph for table. And you actually probably still have, if you have those values still entered in from yesterday, they do recalculate for the new function you typed in. You don't have to retype them in. They're already there. Like mine are already there. Okay, so I see that negative 0.1, the y value is 100. At negative 0.01, the y value is 10,000. And then notice in the table, like mine says 1e6, that e means times 10 to the power of 6. But if you hover over it, so it's 1,000,000. And then those y values are actually the same when it's positive 0.1, 0.01, 0.001. So these y values would also be 100, 10,000, 1,000,000. Okay, so yeah, the question is, what is this approach? A very large number. So we are approaching infinity. Now, couple of ways to answer this question, and this is going along with an understanding of what infinity is. Infinity is not a number. Infinity is an idea. So it is appropriate to say that these limits do equal infinity. So therefore, since they're both approaching a very large positive number, they're both approaching positive infinity, I could say the limit as x approaches 0 of 1 over x squared does equal infinity. However, what this means, this really means if the limit is approaching positive or negative infinity, that actually means the limit does not exist. Okay? Because infinity isn't a number. So when a limit exists, it's approaching a specific value. It will be appropriate, and we actually cover this in the last section of this first half of chapter 2, so 2.5. We actually cover limits that involve infinity like this. I will accept if you say this equals infinity, but understand that the limit actually doesn't exist. If a limit equals infinity, it doesn't really exist. It's just describing what's happening with the graph. So if you actually graph this, I'll do zoom 6 for the standard window. You will even see this on the graph. What this means is that the vertical line x equals 0, or the y-axis, is a vertical asymptote. Okay, so this actually means x equals 0 is a vertical asymptote. Okay, it is possible that you might have a vertical asymptote and from one side you're approaching positive infinity, from the other you're approaching negative infinity. In that case, you would have to say it does not exist because they're approaching different infinities. But it really doesn't exist anyway because they're approaching infinity. All right, so really for this, if you said infinity or you said doesn't exist, they're both correct. Because infinity doesn't exist anyway. Any questions on that? The last example is asking something a little bit different. It gives you a function, f of x equals x squared minus x plus 2, and it says how close to 2 does x have to be to ensure that f of x, or y, is within a distance of 0.1 of the number 4. So limits talk a lot about the idea of closeness. And this question, I realize, might be worded a little strangely. So if I were to put this in symbols, because remember, f of x is just talking about the y values being within a certain distance of the number 4. So this is saying it wants f of x to be within. So I could say within would be greater than or equal to some number, but less than or equal to a different number. And if it's a distance of 0.1 of the number 4, I can take 0.1 less than 4 would be the number 3.9. So this is 4 minus 0.1. And then if I add 0.1 to 4, the y value would be 4.1. Okay, so I'm trying to solve this inequality, figure out what x values, what range of x values do I have so that the y values are within a certain range. So what I'm going to do here is I'm actually going to substitute in the expression for f of x. I'm substituting in the x squared minus x plus 2 for f of x. So this means x squared minus x plus 2 has to be within 3.9 and 4.1. And you might remember solving compound inequalities in algebra and algebra 2, maybe even pre-calc, you review that. However, solving this, we're going to solve it using our calculators. Okay, so you can graph 3 different functions, and it doesn't matter which one is y1, y2, y3. So I'll just make the actual function y1, and then these 2 are going to be horizontal lines, but I'm going to type those in as y sub 2 and y sub 3. Okay, so if I do that, erase this, so I have x squared minus x plus 2. Then I'm also going to graph 3.9, and I'm also going to graph 4.1. And I already have my standard window from before, so I'll just hit graph. And you should see that the 2 vertical lines, or 2 horizontal lines, intersect your function. Okay, but this graph, this is not a great window because these 2 horizontal lines are very, very close to one another. So I'm going to manually change the window here. So for my x values, I'm focused around the x value 2. So I might go, I'll go from 0 to 4. So that 2 is kind of centered in there. And then the y values are really, really close to 4. I'm looking at my horizontal lines are 3.9 and 4.1. So I might go from 3.5 to 4.5. And then if you wanted to change the scale, you could. It doesn't really matter what my y scale is. And if I hit graph, I'll be able to see this is zoomed in more closely. There's my actual curve. That's part of the parabola. And here are the 2 horizontal lines. And what you're looking for then are these two intersection points. So what we're really solving is what x values make the y value equal 3.9 and what x values make the y value equal 4.1, and that's where we intersect. So if I do second trace for that calculate menu, option 5 is intersect. Here you have to be careful. Remember, the left and right arrows allow you to actually move along the curve. If you hit up or down, it changes what curve you are on. So I want to first find the intersection between y1 and y2. So notice right now I'm on y1. So actually, I wouldn't really need to move the cursor. I could just hit enter. And then make sure your second curve says y2, which it does. And I could just hit enter there. I don't need to put a guess in. Just hit enter. But it'll tell me that intersection happens at about 1.966 if I round to 3 decimal places. Okay, so that intersection, I'm going to record that x value 1.966. Now I'm going to find the intersection between y1 and y3. So again, do second trace for the calculate menu, option 5. And I could move up closer to that. So I'm still on y1, hit enter. Now, notice this says y2 again. I already found that one. I should hit either the up or down arrow to make sure that second curve says y3. And then hit enter. And enter for the guess. And that's at about 2.033. Okay, so this means those are the two values x has to be in between. In order for the y values to be between 3.9 and 4.1, the x values have to be that close to 2. Maria?
So for when you like on the graph, you need to do it around like you know what intersection points.
Yep.
You need to do it around that just because it's in number 4.
Yeah, so what I did is I made my x window really, x is really close to 2. So I made my x window from 0 to 4 so that 2 is centered. And then the y values are really, really close to 4. And my two horizontal lines are 3.9 and 4.1. So I made it 3.5 and 4.5 so that it was just zoomed in really close there. Connor, did you have a question? Oh. Yeah. Maybe, yeah. I would definitely change that because AP is gonna require 3 decimal places. All right, the remaining time. Here's the practice for this lesson. That's what you have the remaining time to spend on. We have about 10 minutes left.